Okay, so in the late 60s, continental drift and seafloor spreading were unified into this single theory of plate tectonics, which we refer to as this grand unifying theory of the earth sciences because it explains so many otherwise very difficult to explain observations that workers have been making for decades and really centuries, to be honest. And so this theory says that the lithosphere, which is the Earth's crust, and that uppermost portion of the mantle are divided up into about a dozen individual plates. And those plates have boundaries, and different things can occur at those boundaries. Each plate can contain ocean crust or continental crust or some combination of both. And remember that ocean crust and continental crust differ fundamentally in the chemical composition, really, but that results in different minerals forming that have different densities, really. And continental crust is very low density. It's made up of this very silica-rich composition. We call it felsic. And ocean crust is made up of mafic composition, very rich in iron and magnesium. And so it's more dense than continental crust. Okay, and so if we look at the map of the plate boundaries themselves, we find that there are, roughly a dozen large ones, a few more small ones, but they can be made up of, like this here, the North American plate is continental crust, the continent of North America, and also oceanic crust, right over here. We transition passively from continental crust to ocean crust in the North Atlantic. In the Pacific, we do not do that. On the west coast of North America, the plate boundary does coincide with the continental margin. Continental margin just means where the continent meets the ocean, effectively. And so if it is a plate boundary, we call that an active margin. There's lots of activity there. Whereas if it does not coincide with the plate boundary, we call it a passive margin because there's not a lot of activity. And by activity, I mean things like earthquakes and volcanoes. Right? So this is a map of earthquake distributions, and if you compare that with the tectonic plates, they coincide almost exactly. You can trace out the tectonic plates just based on the distribution of earthquakes. Similarly, you can trace out almost all of the plate boundaries based on the distribution of volcanoes. If we put in mid-ocean ridges as volcanoes on this map, then you really would be able to trace them all. And that's because mid-ocean ridges essentially are volcanoes, really. New crust is being created. It's, thousands of miles of continuous volcanism. And so earthquakes, volcanoes coincide with plate boundaries. Also, the depth of the seafloor, known as bathymetry, that coincides very well with plate boundaries as well, as used as evidence to initially come up with the idea. And so at these plate boundaries, essentially one of three things can be happening. And realistically, as we find when we explore this further, it's really just two things, but transform faults sort of by nature, physics dictates that we need transform boundaries dividing up these divergent mid-ocean ridges. And occasionally, as is the case where we live, just kind of uniquely, because the mid-ocean ridge was subducted, the transform fault actually is the plate boundary. But anyway, I digress. Divergent boundaries are those where the two plates on either side of the boundary are moving away from one another. Okay, and when that happens, it causes melting in the mantle, decompression, basically, decompressional melting, and volcanism at the mid-ocean ridge that creates new seafloor. It is seafloor by necessity because we're melting mantle rocks, which are mafic, very mafic in composition, ultramafic is what we say. Okay, so divergent boundaries are where two plates move apart. Convergent boundaries are the opposite. Two plates are moving together, right? Converging. These are destructive because material is either forced back into the Earth's interior through subduction, or continents will just collide and thicken they'll grow in thickness. But oftentimes anytime that ocean crust is involved, it will subduct. And that's because, again, ocean crust is dense enough, it's similar enough in composition to the mantle to be subducted. Continental crust is not. Transform boundaries are ones where there's not, the plates aren't moving together or away, they're just sliding past each other. And that is kind of a conservative situation. Material is not created or destroyed, generally speaking. And we refer to it as strike-slip motion, a strike-slip fault. So the San Andreas is a strike-slip fault. A right lateral strike-slip fault means the North American plate is going, if you're looking at North America from here, North America is going to the right, we're going to the left. Okay. So we can look at these in a bit more detail. Let's get rid of that thing. The top block is a divergent plate boundary. The two oceanic plates are moving away from one another. A mid-ocean ridge exists and new crust is being created. The middle one is a convergent boundary. There's subduction. This plate is being subducted back into the Earth's interior. There are lots of earthquakes and volcanism associated with that. The bottom one is a transform boundary, like the San Andreas. This is right lateral motion, in fact. And so this block is going that way and this block is going that way. All three of those situations exist. Within convergent boundaries, you can have ocean crust subducted, like I said, or you can have continental crust run into continental crust and just kind of thicken and produce a big mountain range and plateau like the Himalaya. That is the result of the Indian kind of subcontinent colliding with the rest of Eurasia. Okay. We talked about the Benioff zone, this kind of dipping planar zone of earthquakes that exists and was observed long before plate tectonics was established. It would have looked like this in the data set, only without the black lines. This is an animation in the real slide deck. But anyway, there are a variety of things that can happen at a convergent boundary, subduction or not. It can be continental crust and ocean crust or not. Either way, if there is subduction, you're gonna end up with volcanism, and it's gonna form a chain or an arc of volcanoes. Maybe those will form mountains on land, or maybe they'll form islands in the ocean. It can go either direction. But in sum, it sort of looks like this or this. But what you see here, and really, I think it's super obvious on this, is that we really just have two types of boundaries. We have convergent boundaries that have these little square teeth on them, and then we have mid-ocean ridges that have this interesting and unique looking shape. You see that these are convergent, right? The mid-ocean ridges are divergent, but all along the mid-ocean ridge, there are these small transform faults that offset it, okay? And you can see there's a big offset in the mid-Atlantic ridge right here, right? There's a big offset here that is really turned into a transform plate boundary, okay? Similarly, right here, there's an offset in the East Pacific rise that has turned into a transform boundary on the west coast of North America, right? The San Andreas fault system. But the San Andreas originated as a transform fault offsetting a mid-ocean ridge. The only difference here is that the mid-ocean ridge itself went through the subduction zone. And so it was, the relative motion and consequence is that this boundary became a long transform boundary. But that's a pretty unique situation. Mostly what the plates are defined by are either divergent boundaries or convergent boundaries. And so that in sum is, is plate tectonics. Here's a picture of that. So there's this little remnant of the plate called the Juan de Fuca plate that's here next to this ridge axis. And then this transform fault, the Mendocino fault, comes in and becomes the San Andreas, and then it comes out in the Gulf of California and becomes a mid-ocean ridge again. See? Okay, so that's what all of these slides capture. And the net result of this through time is that we have the assembly and breakup of supercontinents. Okay, and so most people have heard of Pangea. Pangea was around about 225 million years ago. It really completely broke up by about 100 million years ago, something around there. The Atlantic Ocean started to open around that time. But moving further back, there were other supercontinents. This is Rodinia. It was around about a billion years ago. And their breakup and assembly have really profound consequences for Earth's surface chemistry, really, because during collisions, continent-continent collisions, tons of material is uplifted in mountain ranges and it weathers really rapidly. Also, when you open ocean basins, there's massive mafic volcanism, these so-called large igneous provinces. And those can have huge impacts on climate, both through CO2 emission during the volcanism itself, and also during the weathering of that volcanic rock. It weathers very rapidly and it has a lot of phosphorus in it, which is a really essential nutrient. We'll talk a lot more about that in the future. But when you weather all of that nutrient-rich rock, it can lead to profound consequences for the climate system. So this is kind of where we're headed, and I think that's the last slide of this slide deck. It says, there's a general first-order relationship between supercontinent breakup, seafloor spreading, sea level, and carbon dioxide levels in the atmosphere. Topic that will certainly emerge in subsequent lectures.